Last week, we talked about an interaction between 2 or 3 electric charges. That interaction was a force. An electric force is that attraction or repulsion between 2 objects, specifically in this case between 2 charges. Let's say you've got a big charge, a big value of charge, and then you've got another one, big charge that's causing the main cause of this interaction. But you got this other smaller charge that's nearby. Both of them will experience the same force, right? Both of them experience the same force because of Newton's third law. But what happens if I take the little guy away? The little charge. Let's draw this out here. Here's the big charge. Okay, it's positively charged. And you get this little guy over here that's negative. What happens if I take this little guy away? There's no force now, is there? And clearly there's no force between 2 charges when you don't have 2 charges. But so the effect of this big charge is gone now, because the effect was the force. But what it produces, what it makes, this influence, mysterious influence that it makes, isn't gone. Just because I took what was experiencing it away doesn't mean what caused it is any different. Let's look at gravity for a second. Just as an analogy here. Right now, picture yourself, just yourself. Nobody else is in the room. It's only you. Okay, you're in the room. You're experiencing gravity. What happens if you leave this room? Does gravity still exist in the room? Sure it does. Right? Well, so how do we describe it if there's nothing there to experience it? To have a force, you have to have a producer, the Earth, and you have to have an experiencer, you. Or you have to have 2 charges to have an electric force. But you don't have to have something to experience it to have gravity or to have electricity. So how do we describe that when you've got nothing experiencing it? We're going to talk about electric fields here. Last year we talked about gravitational fields, the influence surrounding the Earth due to the Earth's mass. Okay, it was there whether or not you were there to experience it. You guys have all heard the old expression, if a tree falls in the forest and there's no one there to hear it, is there a sound? If there's a forest above the Earth and there's nobody there to experience the Earth, is there still gravity there? Of course there is. Right? Gravity's still there, of course, even if there's nothing there or nobody there to experience it, because it's the Earth that causes gravity. We're going to explain that by the use of this fields concept. The field caused by the Earth is still there. It's just the force isn't, because there's nothing there to experience it. Well, gravitational fields surround objects with mass. Electric fields surround objects with charge. So picture the Earth as a big mass of charge instead of a big mass of mass. The gravitational field surrounding the Earth would look like this. The electric field surrounding the big mass of charge would look like this. Oh, wait a second. Just had a thought. What about direction? What about direction? Because we got one kind of mass, right? Positive mass. We have 2 kinds of charge, positive and negative. Well, the electric field surrounding a producer can point outward if it's surrounding a positive producer, or it can point inward if it's surrounding a negative producer. It's like gravity, except it can have 2 directions, whereas gravity can only have 1. Talking about direction, both electric and gravity fields are vector fields. There is a very clear direction associated with them. Look, gravity has to point down toward the Earth. It can't point any other way. It has to point toward the producer. The electric field can point either way, but it does depend upon what kind of producer you have. This is all versus a scalar field, like light, for instance, or heat. Flip on the light switch in the classroom here. Lights off. Lights on. Does that light influence us? Of course it does. Does it influence us in a particular direction? No. Does it move in a direction? Yeah, light travels in a direction, right? The velocity of light is a vector, but the influence of light isn't a vector. The influence of gravity or electric fields is a vector because the influence, there's a direction associated with that influence. We talked about this when we started, right, this lesson. The fields exist as long as there's something there to cause it. If there's nobody in the woods to experience that gravitational field, the gravitational field's still there. There's no force, but there's a field. The whole purpose of fields, right, to explain the influence of something when there's nothing to be influenced by, or nothing to be influenced. Fields exist as long as you have something causing it. Forces only exist if you have something to cause it and you have something to feel it. So there's a gravitational field in the woods if there's nobody there to feel it, but there's no force. There's no force unless there's something there to feel that field, to experience that field. Now, we drew a picture a few minutes ago that looks something like this, right? Positive charge produces a field that looks like this. A negative charge produces a field that looks like this. Why? Well, let me start off by telling you it's an arbitrary definition. Somebody, sometime, somewhere said, this is how we're going to define the direction of the field. I don't know who it was, where it was, or when it was, but it is what it is. Okay, we all have to go by that same convention. The electric field was defined as the way that a positive particle would move if placed in the field. In other words, if I put a little positive particle in that field right there, which way is it going to go? It gets repelled by this positive producer, right? Well, if that positive particle in that field experiences a force away from the producer, then the field has to point away from the producer. Now, even if I take that away, even if I take that positive little charge away, that doesn't mean the field no longer points outward. It does. The field points the way that a positive experiencer would move if it was in the field. It's not in the field now. It was, and it moved outward, away from the positive producer. When I take it away, hey, it's not moving anywhere. But it would move outward still if it was still there. What about over here? Let's put a little positive charge in that field. Which way is it going to go? Goes, see a couple hands moving that way? Yeah, it goes toward the producer, right? That means the field is toward the producer. I could take that away. It's not going to change the field because the field would, that charge would move toward the producer if it was there. We define the direction of the electric field as the way that a positive particle would move if it was placed in the field. Now, we also define it as away from positive and toward the negative, okay, which is really just another way of stating the first way. Kind of just another way of looking at it. All right, let's draw a few pictures. The first two pictures we've already drawn, but we'll draw them again. I've got a positive producer. Hey, remember, the field is the way that a positive particle would move if placed in that field. I put a little positive right here. Where's it going to go? Where's it go? Away. It goes like this. We could draw more field lines. We could draw, in fact, an infinite number of field lines, but they all point away from the producer. Do you guys remember in Physics 20 we talked about the density of the field lines, how close the field lines are together? The closer they are together, the stronger the field. That's a stronger electric field than that. Remember that? I mean, that applied to gravity, right? But the same thing applies to electricity. What if you got a negative producer? Again, this isn't a new one. It's going to look like this, because if I put a little negative charge in there, it's going to move, a little positive charge in there, it's going to move towards it. Oh, I just almost made a mistake, because I said, if you put a negative little charge in there, which way is it going to go? It's not what I meant to say. It kind of leads into a nice question, actually. What happens if I do put a negative in there? Yeah. It gets pushed away, right? Does that mean if the negative gets pushed away, that the field is now outwards as opposed to inwards? Field definition is the way that a positive particle would move if it was there. There is no positive there. Hey, look, there's a negative. It goes away. That doesn't matter, because the field is the way that a positive would move if it was placed in the field. So the negative would move away from it. The negative would move opposite to the field. And the field is still inwards, right? How about this one? Let's go positive and negative together, close enough together that they'll affect each other, perhaps. Look at this, exactly the same as it was before, right? Exactly the same as it was in the diagrams at the top of the page. Right? What's different about it? This is what's different about it. These guys join up. These guys join up. These guys join up. I could draw even more field lines if I wanted. It would look like this. So it's almost the same thing as you see above, but the lines are joining together. Oops, just made a mistake there. Thank you, Chantal. Those arrows should be pointing which way? Inward. Good. Thank you, Chantal. Somebody's paying attention, right? Clearly, it wasn't me. Thank you, Chantal. Yeah, well, or 25. So, or somewhere in between. Let's try another one. Let's go this time positive and positive. I'll go positive and positive here, Chantal, because if I go negative and negative, I'll probably draw them all backwards. Positive goes like this, right? Exactly the same. Right, here we go, kind of in between a little bit here. Just draw a bunch of arrows here. What happens to these guys? They repel each other. These guys repel each other. These guys repel each other. They all repel each other. You guys remember what we said about the density of the field? The further apart the field lines are, the weaker the field is. Tell me what the field strength is right here. Right here. Right smack in the middle there. It's not really a trick question. Kind of an easy one. What's the field strength right in the middle? Right where the field lines all repel away from. There is no field strength, okay? Let's say we got those two positive charges, and I put something in the middle there. It experiences a force to the right and to the left. What's the net force? 0. What's the field? 0. How would this change, by the way? How would that picture change if it was two negatives instead of two positives? What would stay this? What would stay the same about it? Yeah, I mean, the shape would be the same, right? What would be different about it? Derek, what would be different about it? Well, yeah, the producers would be negative, yeah. Can you look a little deeper, maybe, than... yeah. Yeah, fields would go the opposite direction, right? I got one more picture to show you. So this time we got two conducting plates that are charged. Man, the last little bit, we were talking about the electrostatic precipitator and painting the fence with an electrostatic paint sprayer and all these more practical stuff. Now we're talking about two charged plates. Like, boy, did we ever go from practical to non-practical, okay? There will be applications to this stuff. But for now, let's just assume we have two plates, two flat conducting plates. One's positive, one's negative. If I was to put a positive charge right here, where would it go? Go ahead. Good. If I put one right here, it would go towards the negative, and here towards the negative, and here towards the negative, and here towards the negative. So the electric field here is from positive to negative still. Shaped a little bit differently, though. What do you notice about this shape compared to the other ones? These guys are parallel, right? Equidistant apart. These are all over the place, right? These are all what we call non-uniform fields. The field varies wherever you are, right? The field is weaker over here. The field is stronger over here, okay? The field is weaker right here. The field is stronger right here. What about this one? This is what we call uniform electric field. That's a symbol for electric field, by the way. Uniform electric field. Lines are parallel to each other. The exception to that, right at the edges, they kind of curve around like this. We call those the edge effects. That's a non-uniform electric field at the edges. But you know what? We don't really care that much about the edges. When we do an analysis of this, we're always going to look at in the middle, in between them, where the field is uniform. So remember that. And it's going to rear its ugly head tomorrow in tomorrow's lesson. Difference between a uniform and a non-uniform field. Okay? These are all non-uniform. This is a uniform field. Right? Just out of curiosity, talked about there are practical stuff to this, practical applications. Where have we seen something like this earlier today? The question with the cloud on the earth. We induced a temporary separation of charge in the earth to make the earth positive. Look at that. This is a perfect, perfect case scenario, but describes pretty well what we observed earlier today in that multiple choice question, the whole idea of lightning forming between the cloud and the ground. There's other places too, but just so you can see that there is something, somewhere, that this actually applies to.